Let's take a look at example 9.13. It says use equation 9.3, which I have written here, and compare the result with that obtained using equation 6.18 to calculate the enthalpy of the reaction for the process shown here. So we're going to take hydrogen and combine it with chlorine, and we're going to end up with 2 moles of HCl. So if we think about what's happening in this reaction, we're starting out with 1 molecule of hydrogen in the gas phase. And when we look up the bond enthalpy for the H2 bond, we see that it's 436.4 kilojoules per mole. That means it takes that much energy, 436.4 kilojoules, to break all the bonds in 1 mole of H2 in the gaseous phase. So if I look up the bond enthalpy for Cl2, and we'll write out the Lewis structure for that because we need to break the bond between the 2 chlorine atoms, we see that it's 242.7 kilojoules per mole, and then of course we're going to form a bond, and we're going to form 2 bonds between hydrogen and chlorine. So we're going to make 2 HCl bonds. I'll write both of them out here, and each one of those has a value of 431.9 kilojoules. So when we form that HCl bond, we're going to release 431.9 kilojoules per mole for every mole, and since we're forming 2 moles of HCl, we're going to multiply that by 2. So this equation that we're going to use here is reactants minus products. Why? Because when we're dealing with the reactants, we have to put energy in, right? We're putting energy into the system in order to break this bond here and in order to break that bond there. When we form our products, we're going to get energy released. And so since energy is going to be released, we're going to subtract the amount of energy that it takes to break these, right? We're going to do the opposite. We're going to form bonds instead of break bonds. So when we plug in some numbers into our equation, we get that delta H of our reaction is going to be equal to the bond enthalpies, or the sum of the bond enthalpies of the reactants. So that's 436.4 kilojoules per mole. I'll leave the units out and put them in at the end, plus 242.7 kilojoules per mole. Then I'm going to subtract 2 times 431.9 kilojoules per mole because I'm forming 2 moles of HCl. So we'll put all that in there, and then we'll put kilojoules per mole. And when we work out the delta H of this reaction using bond enthalpies, we get that it is negative 184.7 kilojoules per mole. If we were to use equation 6.18, and I have it laid out here that the delta H of our reaction is going to be equal to 2 times the delta H of formation of our products minus the sum of the delta H of formations of our reactants. Now remember, this equation is set up as products minus reactants, so it's the opposite of equation 9.3. Why? Because delta H of formation, when we form something, generally speaking, it's going to be an exothermic process. Energy is going to be released. And you can see that when we plug the numbers in, we end up with negative 184.6 kilojoules per mole. And so you can see that there's a little bit of variation between the delta H calculated using bond enthalpies and the delta H calculated using heats of formation. The small discrepancy here is due to differences in rounding off. Question 9.14 asks us to estimate the enthalpy change for the combustion of hydrogen gas, which is shown right here. H2 plus O2 gives us 2 moles of H2O. We basically follow the same procedure that we did in example 9.13. Note, however, that H2O is a polyatomic molecule, so we're going to need to use the average bond enthalpy value for the oxygen-hydrogen bond. Here I've written down the equation that we're going to use to calculate our delta H for this reaction, and I've written the Lewis structures of all the reactants and the products. So if we think about the bond enthalpies of the reactants, we're going to have to put energy in to break the hydrogen-hydrogen bonds and to break the oxygen-oxygen bond in H2 and O2 respectively. If I look at the bond enthalpies of the hydrogen-hydrogen bond, it's 436.4 kilojoules per mole, and the oxygen-oxygen bond is 498.7 kilojoules per mole. Since I have 2 moles of hydrogen, I'm going to multiply 2 times 436.4, and I'm going to combine that with my oxygen-oxygen bond strength, which is 498.7. And then I'm going to subtract from that the bond enthalpies from my products. What are the types of bonds in water? I have 1, 2, 3, 4 oxygen-hydrogen bonds. So I'm going to subtract 4 times the bond enthalpy of the oxygen-hydrogen bond, which is 460 kilojoules per mole. So I'll take all of this and I'm going to put the whole thing inside of the units of kilojoules per mole. And I've already gone ahead and done the work here, and we get that our delta H for this reaction is equal to negative 469 kilojoules per mole. The reason we can say that this is an estimation of the enthalpy change for this reaction is because the bond enthalpy for the oxygen-hydrogen bond is an average.